so we're going to do an example, and I give you choices. We have a baseball player. We have a stunt person. Or we have a battleship.
Oh, battleship, definitely.
Is that okay? All right. All right. So we have this battleship, and it's. Everybody watch The Last Ship?
Yes.
Kind of like that?
Oh yeah.
Oh, yeah.
Oh yeah, buddy.
So we got cruiser. So we have a little radar beacon there. Bridge. Okay. It's kind of a short ship.
Yeah, it's kind of.
Oh, hey, wait, make it a little longer. I'll put the chopper on there because it's a destroyer, right? Yes. It's a destroyer, okay? All right, and then on the other side of a mountain. Wow. We're shooting at a target, another ship. Should make it like that alien ship that invaded.
Yes.
Right?
Oh, is it
Battleship.
the
Yeah.
Battleship.
Yeah.
Wow. Oh,
It's eyes.
giant lasers. Giant lasers. Okay. And we know that it's 2,500 meters from the main gun to the mountain peak. There. Okay, it's 2,500 meters there. It's 610 meters to the mean old bad alien thing, spider creature thing in the water. And it's the peak is 1,800 meters from the water level to the peak. Okay. And the ship fires a shell at a 75-degree angle. And the velocity of that shell is non-trivial. The velocity of that shell is 250 meters per second. Sound effects are optional. Okay? Two questions. How close to the enemy ship does the shell land? And how close to the peak is the shell? It's a G-rated class. That guy's not going to get hit. We're scaring him away. Get back! Go back! We're going to show our military might, but we won't sink you because we're tolerant. Yes, 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 yes. Okay. How do we go about doing this?
Find the vector components.
Vector components, I agree. Okay. So start by drawing that shot. Am I still on camera? Can you still see that?
Yes.
Yeah. Okay. So we're at 75, that's not 75 degrees. Try again. There, that's better. I'll live with that. 250. Okay. How do I find the components? What do I do?
Sine of 75 times 250.
Okay, so 250 times the sine of 75. Is going to be equal to which velocity?
The Y.
The y, correct. Vy initial. True or false, that's going to stay constant.
Yes.
The
No.
y component of the velocity is not, it is. Which is it?
It's not.
It is not. Why? Why? Gravity. So, I like to always write this on my page somewhere. It's G-rated. All problems on the earth are G-rated, okay? Is that it? Is that all I'm gonna do?
Yes.
That's all I need?
No,
No.
find the X.
Yeah, we gotta do the X component, don't we? So we got the Y component, so now we need the X component. Ooh. Okay, I'll do that one. There we go. There. So how am I gonna find that X component? This is the Y component. How's the X component?
Cosine.
It's gonna be cosine function. So then I should take 250 times the cosine, yeah, there we go, of 75 degrees, that's equal to Vx initial. Hey, and then I'm gonna get two values for that. Two values. Anybody get the Y yet?
241.5.
241.5. 241.5 meter per second. And the X?
64.7.
64.7. Will that one stay the same?
Yes.
Yes, because we are going to ignore air resistance, right? So then the horizontal components can stay the same. And there's no acceleration sideways, right? Now, if we used a cruise missile, it'd be different, okay? Because there'd be a rocket pushing that thing. Okay. Okay, what do I do with that? What do I do with that? Could I figure out the range?
No, because you don't have time.
We don't have time yet, do we? Do we know for certain that the shell will be at its halfway point at the apex? Do we know for sure that the shell is going to be at the apex of its motion at the top of the cliff? No. No, we don't. Yeah.
But just based on the displacement of X, can you assume that that the apex is not gonna be over the peak?
I think the apex, well, if the shell's going to clear the mountain, it's probably going to be higher, right? Well, not necessarily. It could be on the way down. It could be on the way down. We're not really sure where that's going to happen, are we? Could we find the altitude of the apex? I think we could. Oh yeah, I think we could. We had four equations we worked with. What were they? Vf is equal to Vi plus At. Delta x is equal to 1/2 of Vf plus Vi times t. Delta x is equal to Vit plus 1/2 At squared. And Vf squared is equal to Vi squared plus 2A delta x. I suggest that we could find the maximum altitude of this projectile. Yeah. What's this going to be at the apex?
0.
Good. Do we know that?
Yes,
Do we know that?
yes. Yes,
We don't know that,
we don't.
right? So we said Vf in the y squared is equal to Vi in the y squared minus 2g delta y. Remember, we translated those four equations for y direction. So if that's 0, can somebody tell me what the maximum altitude of the projectile is? Bet you can. Who's got it? Somebody with a calculator. There's more up in the box too if you want to grab one. Help yourself. What do you get? Hey, I realize the question doesn't ask this. I'm just posing a scenario. We could find the apex of this projectile if we wanted to. Maybe we can get confirmation too once one person's got it. I wrote that backwards, didn't I? Vy initial squared. There we go. That's it. That'll help better. Better be consistent, otherwise I'll confuse you. 241.5 squared divided by 19.62. Is it a big number?
$2,972.6.
So what-
Meters, right?
2 times gravity.
That the same number? Anybody else? I'm not saying you're wrong, I'm just saying. Got that? Okay, I think we can go with that number then. Questions on how I got that? My Vy initial is here. I use the fourth equation. At the apex of the motion of the projectile, the y component of the velocity is 0. It's at its peak, you can't go any higher. So that's known, that's 9.81, we solve for that. Right now, it looks like we clear it, right? The apex of the projectile is gonna clear it. Question is where? What if we treated this one like we did the football problem? What did we do in that football problem yesterday? How did we figure out the time it would take to reach the crossbar? What did we do?
Use the X component.
We used the x component. Because if we know the x component of the velocity, we know the range, we will find the time at the peak. Now, obviously, we're not shooting through a mountain, but remember that x component's gonna stay the same throughout that projectile's motion. Pretend like those are the same lines. So even if it is crossing over top of that cliff, or the mountain top, it's still gonna have the same velocity horizontally. So the time it takes to go from the gun to the center of the peak vertically measured horizontally at 2,500 meters, we can find the time. So what's that gonna be? I think we go with number 2 or with number 3, remembering that the acceleration is 0. There is none. So delta x then is gonna be equal to what? Third one, horizontally we've got no acceleration, right? So that means it's just gonna be Vx times the t. The initial velocity in the x times t. Because that's the same as the final velocity in the x, right? So then 2,500 is known. Vx is known. Solve for t. Anybody?
38.64.
38.64 seconds. So that's the time to the peak. Can we now find the altitude of the projectile? I think we can. Go with equation 3. But write it in terms of y, the vertical components. What do we do? Red there. Delta y is v, how are we writing that? Y initial t minus 1/2 gt squared, correct? Do we know what the t is? Yeah, 38.64 seconds, right? Do we know what the initial velocity is? Yeah, right there. And we know what g is. So we'll have 241.5 times 38.64. Now if we just computed that part, we would find its vertical displacement in the absence of gravity. That would be going straight up. But because we have gravity, we're gonna have to take away from that displacement gravity times the square of the time. It's like velocity times time, right? Okay, so we subtract then half of 9.81, 4.905. I just took half the value of gravity, just write it as half its value, times 38.64 seconds, and that's gonna be squared. Anybody have that vertical height? Let's check it. You got one there?
2008.15.
Meters. Somebody double check that? Again, I'm not saying you're wrong, I'm just saying we wanna check it. We got it? Okay. So did we clear it? Yeah, we did. We're somewhere up here, right? So we answered the second question already, and that's gonna be on the order of 208 meters, right? It cleared it by about 208 meters. Okay, now, does it hit its target? That's a little tougher question, because we still don't know if it's at the apex, do we? But listen, I think we could find the time it takes to get to its apex. Let me draw the picture for projectile motion again. This entire path of the projectile is going to look like something like this, right? Up and then down. I don't know if it's short, I don't know if it's long, I don't know if it's gonna drill the ship, whatever. But would we agree that that's the path? At some point, the vertical velocity is going to be 0. We used this equation a moment ago, where is it? Here, to find the maximum altitude. Okay? What if we used this equation here, the first one, and solved for the apex time? That is, the time it takes to the vertical velocity goes to 0. Does that sort of make sense what I'm saying? I want to find the time that it takes to get to here. And if you remember from the sketch we made yesterday, at this point the y component to the velocity is 0. It's not 0 here at the start. At the start is 241.5, at the peak it's 0. So there I know an initial velocity, I know a final velocity. Gravity is acting. What's missing is t. So yf is equal to vyi minus gt. Negative because gravity's down. We said that this is 0 at the apex. We know the initial is 241.5 minus 9.81 times t, a meter per second squared. What's the time it takes to get to the apex?
24.6.
24.6 seconds. That's the apex. Oh, interesting. I think that's interesting. How long did it take to hit the peak? 24.6 is the halfway point, right? So is that shell on its way up or on its way down? Down. And you know what? We can actually figure that out by the sign of the velocity at that point. That's very interesting. Very interesting indeed. This represents half of the time the projectile is in motion, right? So in the first point, that's 24.6 seconds from here to the peak. So what's the second half of the motion going to be? How long will it take for the second half of the motion? 24.6. Now I didn't really draw that to scale. That was sort of bad because this should be before. I think you see what I'm saying. The peak is more like over here and then it's coming down, right? So that, but the first half of the motion until the velocity is 0 is 24.6. The second half is 24.6. And so then the total time is what? 49.2? 49.2 seconds. 2 seconds. What can I do with that now? If that's the total time in the air, and the projectile is starting and ending at the same height, we're assuming that because both are at sea level, okay? But that's the total time in the air. Now I can find the total range. In the same way that I used this equation here to find the time to the peak. The delta x is Vx initial times t, which we said is 64.7 meters per second times 49.2 seconds. Does anybody have an answer there? How far then did it go horizontally? Anyone just call it out?
3,183.
3183 meters?
124, yeah.
Can we get confirmation on that?
Yeah.
Okay. So what's our total? 2,500 plus 610. That's 3110, isn't it?
That's 124, I think.
This one's 0.24?
Yeah.
Okay, sorry. 0.24. Okay? Range is 3110. Where did we land? Pass. Splash. Warning shot. There's lots of ways we can solve these. We can develop some very complicated equations to make it simpler. And I might show you a little bit of that on Monday, but right now this is the easier way to do things. Okay? All right, that's it. That's time.